In this chapter's videos, we are really going to be looking at and focusing on the atom. So the atom consists of a bunch of tiny little parts, and so we're going to look at each of these parts in a little detail. So the nucleus is a tiny region in the center of the atom. It contains protons and neutrons. And these protons and neutrons make up almost all of the atom's mass. So if you look over at the diagram here, this center cluster is the nucleus. And you can see the neutrons are the blue spheres and the protons are green with a plus sign. So in the nucleus, the protons and neutrons are jam-packed together, and so that gives most of the mass. However, it is just a tiny piece of that atom. So if the atom were the size of a football stadium, the nucleus would be about the size of a pea. Protons are positively charged, and they are located inside the nucleus. All protons are identical. Let's see. The number of protons gives different elements their unique properties. So each element has a different number of protons. So another way to think about it is that no two elements or no two atoms have the same number of protons unless it's the same element. So again, protons are positively charged and they're located inside the nucleus. Neutrons are electrically neutral, or they have no charge. Again, they're also located inside the nucleus. Oftentimes, there are the same number of neutrons as protons. The last part of the atom is the electrons, and these are negatively charged. And they are located outside of the nucleus. So the charge is equal and opposite to the charge of a proton. So atoms have the same number of electrons and protons, so they're considered electrically neutral. They don't have a charge to them. So basically it's like saying we have a positive 5 and like a minus 5, and if you do the math, it equals 0 or neutral. So the positive 5 would represent the protons, the negative 5 represents the electrons. So because we have these opposite charges, the positive protons and the negative electrons, we have some opposite charges attracting one another. So the negative electrons are attracted to the positive protons. The force of attraction keeps the electrons moving around the nucleus. And then particles with the same charge repel each other. So we get this thing called the strong force. Then the strong force is the force of attraction between protons and neutrons. This is stronger than the electrical force that pushes the protons apart. And it's only going to affect nearby particles. It's not effective if the nucleus gets too big. So it's kind of got the just right size. Because it puts an upper limit on the number of protons an atom can have and remain stable. So if you look at the diagram, the strong force affects particles that are near each other. So these two are super close by. And so then the strong force, notice this particle and this particle, they're too far apart to be affected by the strong force. The atomic number and the atomic mass. So most of the atom's mass comes from the protons and the neutrons. And electrons have almost zero mass. They don't have much mass to them at all. So we pretty much don't even talk about them in terms of mass. And so when we measure the mass of an atom, we look at something called the atomic mass unit, or AMU. And that's the SI unit for the mass of an atom. 1 AMU equals the mass of a proton, which is approximately 1.7 times 10 to the negative 24th grams. The convenient thing is that 1 neutron also has the mass of 1 AMU. So the mass of 1 neutron equals the mass of 1 proton. So to figure out the total mass of an atom, you simply add the number of protons plus the number of neutrons together, and that gives you the total mass of the atom. The atomic number indicates the number of protons that an element has. It is unique for each atom and each kind of element. And so this is the whole number on the periodic table. So for example, down here, your atomic number for helium is 2. The mass number is the number of protons plus the number of neutrons. And this is equal to the atom's mass in atomic mass units. So the mass number, a lot of times you'll see it written in this top left corner, and the atomic number is written right below it. And so most helium atoms have 2 neutrons, so the mass number is 4 from 2 neutrons and 2 protons to give us a total of 4 AMU. So let's practice this. Let's say an atom has an atomic number of 12 and a mass number of 24. How many protons and how many neutrons does this atom have? So remember, atomic number means number of protons. So if our atomic number is 12, in this case, this atom has 12 protons. So then we look at our mass number, and the mass number equals the number of protons plus the number of neutrons. So in our case, we know the mass number is 24. Because of the atomic number, we know its number of protons is 12. And so that allows us to just solve for n. So we just simply subtract 12 from each side. Oops, sorry, not divide. And we get that we have 12 neutrons. So in the second example, an atom has an atomic number of 8 and then a mass number of 16. Alright, so since the atomic number is 8, we know that means that this atom has 8 protons. And then we use our little formula. Mass number equals the number of protons plus the number of neutrons. And so we can plug in what we know. We know our mass number is 16. We know we have 8 protons. So we can solve for neutrons by subtracting 8 from each side. I did it again, didn't I? Subtract 8. And so we get that there's 8 neutrons as well. So ions are a little different than atoms. Ions are either positively or negatively charged. And this is because they have either gained or lost an electron. The number of protons and electrons in an ion are not the same. An atom that loses electrons are positive ions, and we refer to those as cations. And those atoms that gain electrons are negative ions, and we call those anions. So for example, here a fluorine atom has 9 protons and 9 electrons. So this one is electrically neutral. Whereas here it's gaining an electron, so now we have a total of 10 electrons and 9 protons. Since there's one more electron, we now have a negative charge, and we indicate that when we write fluorine symbol by this little negative sign up in the top right corner. So fluorine, when it becomes an ion, it actually becomes an anion because it has that negative charge to it. Another situation that we could have is called an isotope. This is an atom of an element that has a different number of neutrons from other atoms of that element. So, for example, some carbon atoms have 7 or 8 neutrons instead of the usual 6. So many of these isotopes for different elements occur naturally. And so usually there's 1 or 2 isotopes of an element that are most stable and can be found in nature. Different isotopes of an element will generally have similar chemical properties because they have the same number of protons and electrons. The only really big thing that'll be different is their mass. So, for example, hydrogen has 3 isotopes. So hydrogen is the most common isotope. Most hydrogen atoms have 1 proton and they have 1 electron, but they will have 0 neutrons. Hydrogen's second isotope, called deuterium, will again have 1 proton, has to have 1 proton to make it hydrogen. It will also have 1 electron and 1 neutron. So notice, maybe I should do them in a different color. The number of neutrons is changing. So tritanium is a hydrogen atom with 1 proton and 1 electron, and then it would be 2 neutrons. So here we have some images for you showing hydrogen having the 1 proton and the 1 neutron, the 1 electron, and then 0 neutrons. And here, deuterium, 1 proton, 1 neutron, 1 electron. And lastly, tritanium, 1 proton, the 2 neutrons, and then the 1 electron as well. And so the prefix tri means 3, indicating its mass number. Du means 2, again matching with the mass number. So when we name isotopes, they're usually named for their mass number. So for example, carbon with 6 neutrons has a mass number of 12, so we call it carbon 12, and we do write it with this dash right here. So what would we call carbon when it has 7 neutrons? So to answer that, we have to figure out the mass number. So remember, the mass number is the number of protons plus neutrons. And in this case, it's telling us we have 7 neutrons, and carbon always has 6 protons for a mass number of 13. So a carbon atom with 7 neutrons would be called carbon 13. And so isotopes are often used to estimate the ages of rocks and fossils. So up until this point in science, you have been told that protons, neutrons, and electrons are the smallest parts of an atom, which is true. However, what makes up protons and neutrons? And these are called quarks. Quarks are particles of matter that make up neutrons and protons. These quarks are smaller than any proton, neutron, or electron. And so in order to make a proton and a neutron, you need 3 quarks. So it takes 3 quarks for every proton and 3 quarks for every neutron. The charges of quarks are balanced to give protons a positive charge to a proton and a neutral charge to a neutron. So the 3 quarks that make up a proton could be positive, positive, nothing. Could be positive, positive, positive. And so a neutron would be no charge, and no charge. Quarks are never found alone. They're always paired up or have 3 of them together. And they're only found as components of other particles. So gluons are things that hold the quarks together. I think that kind of makes sense because of the glue in gluons. They make quarks attract each other more strongly the further apart the quarks get. So that would be like if you imagine holding a rubber band between your fingers. If you try to move your hands apart, they will be pulled back together by the rubber band. The farther you move your hands, the stronger the force of the rubber band pulling your hands back together is. So gluons work in the same way inside protons and neutrons. They're constantly pulling together. So if you move your hands apart enough with enough force, the rubber band eventually breaks. And this is the same as true for quarks. You pull them far enough apart and that force will eventually break. If given enough energy, they will pull apart with enough force to break, the binding from the gluons. The energy that is put into a particle to make this possible is then used to create a new set of quarks and gluons, producing a new proton or a new neutron. So quarks were first proposed in the 1960s, and there are 6 different types of quarks. So you can see those 1, 2, 3, 4, 5, 6. They're very hard to study because they're so small, and they're very, very expensive. So just new for your bank of knowledge is that protons and neutrons actually have smaller particles that make them up, and those are called quarks. And gluon actually holds the quarks together.